Assalamualaikum and hi everyone. My name is Siti Hanani Hafizah binti Syekh Anwar and my matric ID is 2410912220. Today, I will be presenting our finding for Lab 2, Operational Amplifier. Our main objective was to investigate the fundamental characteristic of various op-amp configuration, compare theory with our anti-spice, simulation result, and critically analyze the practical limitation of the device. First, inverting amplifier circuit. Inverting amplifier circuit schematic and clip waveform. Let's begin with the inverting amplifier, which yielded our most critical finding. We configure the circuit with an input resistor of 1 kilo per omega and a feedback resistor of 33 kilo per omega. Theoretically, this gives us a gain of minus 33 with a 1 volt peak input. The expected output should be 33 volt peak. However, as you can see on the waveform, the output is severely clipped or flattened at approximately 14 volt. This deviation is crucial. It confirms the principle of saturation. The op-amp cannot accept the 15 volt supply voltage, proving that high gain must be balanced against the physical limit of the device. This phenomenon is a primary example of a real-world constraint. Second, non-inverting amplifier. Non-inverting circuit schematic and in-phase waveform. Moving to the non-inverting amplifier using RF 10 kilo per omega, our calculated gain was 11. The simulation matched theory perfectly, yielding an 11 volt peak output. Crucially, the input and output signal are in phase, confirming the lack of a 180 Celsius phase shift, unlike the inverting configuration. Third, integrated circuit. Integrated circuit and square two triangle waveform. The integrated circuit will successfully confirm its mathematical operation. The 1 volt square wave input was transformed into a triangle wave output. The main analytical point here is the inclusion of the large 10 mega per omega feedback resistor. The resistor on the schematic, it is a compensation technique. Its purpose is to manage tiny input bias current and prevent DC drift, which would otherwise push the output into saturation very quickly. Fourth, differential circuit. Differential schematic and triangle to square waveform. The triangle wave input was successfully converted into a square wave output. Here, we focus on the 100 picofarad capacitor placed in parallel with the feedback resistor. Its component is a critical solution to a real-world problem. The ideal differential is very sensitive to high-frequency noise. The 100 picofarad cap acts as a filter to stabilize the circuit and prevent output oscillation, showcasing a key design trade-off. Lastly, summing amplifier. The summing amplifier using 10 kilo and 2 kilo input resistor. We verified the output is the weight inverted sum of the two 1 volt sine wave input, resulting in a minus 6 volt peak output. Our analysis here addresses the high frequency limit. If the source frequency is increased too much, the output signal will distort because the op-amp internal slew rate cannot change the output voltage fast enough. It is another crucial practical constraint. Overall, we successfully verified the operation of all 5 op-amp configurations. However, the biggest finding was the inverting amplifier, where high gain caused severe output clipping because the voltage exceeded the saturation limit of the supply rail. To handle practical design issue, we had to introduce specific component, a 10 mega per omega resistor, stop DC drift in the integrator, and a 100 picofarad cap managed high frequency noise in the differential. Ultimately, this experiment shows us that successful analog design is always about balancing ideal theory with the real world device constraints, particularly regarding slew rate at high frequency. Thank you.